Welcome to the third episode of EVM programming course. In this episode, we will describe opcodes and precompiles, which are core to the EVM transaction execution. But before digging into opcodes, let's first deal with the bytes, shall we? So you probably know that everything in digital space is 0 or 1. This was picked because it was the easiest and most reliable way of transferring data and has close resemblance to the machine and the transistor consisting of the processor. So either the current is flowing and we consider it as 1, or it's not flowing and we depict this as 0. Now we can encode all kind of information this way using stream of zeros and ones. For example, if we chain together a few of the values, we are getting, some stream of bytes, and we can actually treat it as a number. And actually the same goes with decimal numbers. So let's take, for example, this number. So we are used to this notation and how it looks like, but you probably never thought that we can actually depict this format a bit differently. It will still have the same meaning, just that its representation will be a bit different. So actually what you can do is to represent the same number by splitting each of the digits in respective place. So for example, we have number 3 and we multiply it by 10 to the power of 0. 10 to the power of 0 is 1. So it will give us 3. And we add it to the second digit, but this time 10 to the power of 1, which gives us 90. Next digit, 4, we are multiplying it by 10 to the power of 2, which is 100. So we have 400. And so on and so forth. So we can describe this number also in this way. This is just a different notation. And this is very useful because this is just a generalization of how we perceive the numbers. Having that, what if, for example, we are not using the 10 as our base, but we are using, for example, 2 as our base? So as you can see here, the same goes for the binary. We can represent that. The similar matters here, but we are not using 10 as our base, but our base is 2, because in binary we have only 0 or 1. And this is how we can represent a stream of bytes as binary. So as you can see, the same goes for different notations. So we have binary, we have our decimal, we have octal, we have hexadecimal, and this is just a matter of expressing numbers in different ways. One additional thing to add here is that you can see that if your base is bigger, you need less characters to convey the same number. And for example, if we take this number from our example and put it into chisel, we see that this is our number, but in hexadecimal representation, that is this number. So this is the same number, however, represented just in different format. And as you can also see, the hexadecimal has this special OX. So if you see this OX, that means that it is hexadecimal representation. Apart from that, the second really common denominator is binary, which starts with 0B. In case of Ethereum, this representation is unsupported, but normally you can encounter that when concerning binary, and we will also be using that later. So yeah, for example, also we have cast, which is super great tool. This is one of the 3 main tools of Forge. This is not in scope of current course, but you should definitely check that out if you haven't already. So as you can see, we have the same number in different representation. We may also have octal representation. We can actually, we cannot. So there are like only the most common are supported, but using this general formula, we can encode any information, having any bases that we want. Okay, one more important thing to add here. We have two ways of writing sequence of bytes, and this is Little Endian and Big Endian, and they differ in the order in which they write bytes. So for example, having this number, it will be represented differently using Little Endian and Big Endian. So the same number will be depicted in the same way in Big Endian, and its order will be swapped if we are talking about Little Endian. So in case of Ethereum, it's using Big Endian, which in my personal opinion is way better to read, and probably it was chosen because of that. And last thing, before we move on, I mentioned already multiple times that single word has 32 bytes. And you also saw this in stack memory storage, that this is basically the only type that EVM supports. And the question is why this particular value was taken by EVM. So we can find the answer in yellow paper, saying that the word size of the machine and thus size of stack items is 256 bits, which is 32 bytes. This was chosen to facilitate the Keccak 256 hash scheme and elliptic curve computation. It also goes into explaining the memory model and stack model, which we already discussed. We will not go through it. You can just see that it is here if you want to read it yourself. I also heard Vitalik Buterin in one of the interviews saying that they were looking for a number that is big enough to fit all the use cases and small enough not to bloat the storage with unused data. Okay, having bytes already covered, let's go through the opcodes. So the opcodes, or operation codes, are low-level instructions that the EVM understands and executes. They are building blocks of smart contracts. They're the same to the EVM that machine code being executed by the processor is to your computer. And just like your computer only talks assembly code, node running EVM code only use low-level opcodes. So you may ask why they're not called assembly. Well, first of all, they're not machine code that your hardware understands, but rather a virtual machine code. And second of all, due to the decisions made when designing EVM, some of the opcodes are performing multiple operations unlike normal assembly does. For example, Keccak opcode performs hundreds of atomic operations in order to hash array of bytes, which is passed to it. So we have well-defined amount of opcodes, which are supported by each EVM implementation, and they have to be the same in all the implementation in order to make sure that everyone executes the same code, hence has the same state. Because as I already discussed in first episode, every node needs to reach the consensus on what is the current state. And if some of the nodes were executing the smart code in a different way, that would lead to different storage, and hence the world state would differ between these different implementations, which would actually result in chain split, because some nodes would think that this state is correct and the other state is incorrect, and like the other part would say the otherwise. Now let's discuss what types of opcodes we have. We're gonna use EVM yellow paper for that. So the opcodes start with the stop and arithmetic operations. And this is really super important. All arithmetic is modulo 2 to the power of 256. So EVM defines that in case that overflow or underflow occurs, this is treated as modulo. So if you had, like, for example, 2 to the power of 256 plus 1, it would be the same as you did the modulo of this. So this was wrap up again back to the 1. And this is less important, but the 0 power of 0 to the power of 0 is defined to be 1. Okay, so first one is stop. Whenever the EVM executes code and sees this particular opcode, it just stops executing. No matter if there is any code after this stop, it will just finish execution. Next, we have, as you can see, arithmetical operations. You can see this really strange notation. Unfortunately, this is the language that Yellow Paper uses. It uses very technical language and is not fun to read. That's why we'll use the Beige paper, which is a version of Yellow Paper that just strips down all of this very specific language and makes it easy for normal people to understand. So this format is a bit different and has some additional information. In this case, we have the gas cost connected to each of the opcode. We have information how much stack elements it takes and how much stack elements it puts. So let's see that in this example. We are pushing 2 elements and you can see that we have both of them on our stack, and then we execute add, and what we are left with is the result of the addition, and we like the 2 elements from the stack disappeared and 1 new element appeared. So this is what it means. It takes 2 elements, top elements from the stack, and it outputs 1 new element. Then we have multiplication, subtraction, division, which is well known by you. And now this is interesting because we have different operations for division and line division. Why is that? So in order to show you that, I created a test function that all it does, it subtracts whatever we pass to it from 1 and it returns it at byte 32 just to show you how the underlying representation of negative number is. If I execute this function with 0, well, you guessed it, we have a bunch of zeros and 1 at the end because 1 minus 0 is 1. If we pass 1, we should get 0, and this is what we get. But what if we pass 2, for example? If you pass 2, this value will be minus 1. So how does Solidity represent that? As you can see here, it is being represented as the biggest possible number. And why is that? Well, in order to represent negative number, we have to come up with some idea how to do it efficiently. And EVM uses 2's complement notation for that. And this was just their design decision. They made it so if we have signed operations, we have specific opcodes for them because we have to know if the number is negative or not. And they decided that using the 2's complement notation will be the best. But okay, so now minus 1 is treated as this really huge number, 2 to the power 256. But what if we use like 3? What will change? As you might guess, it is subtracted. So the bigger number I'm passing here, the more is being subtracted. So if I actually pass this big number, so if I pass a bunch of F's, I will finally go to the number that is very close. So this is super close to, like, we can see that it's like way closer to 0, but actually is way bigger. Next we have modulo and as well signed modulo, as I just described. Next we have add mod and mul mod. Those let you perform operations that first add and then perform modulo on the addition and so on and so forth. Why it's useful? Because the 2 added values can overflow 2 to the power 256 and they still will be counted as if the overflow didn't happen. Next we have exponentiation, sign extend, which is extending the length of 2's complement signed integer. So as I said, 2's complement, this is just a way of saying how the EVM is treating negative numbers. Remember, starting from counting from all the F's and going down from there. Then we have comparisons, again, dividing by signed and unsigned, checking if it's equal, if the bytes are 0, and next logical operations and or XOR, and finally retrieving a single byte. So next, under 20 and hexadecimal, we have just only 1 byte code. This is SHA-free, or in case of EVM, the specific implementation of SHA-free, which is Ketchak 256. Next, under 30s, we have some useful environmental information. So first we have address, which is address of currently executing account. So because in order to execute any opcode, it has to be smart code. So only smart code address can be returned here. Next up, we have balance, origin, which is transaction origin, caller, which is message sender in Solidity, the value that we pass together with the message value. Next, we have operations on call data, size of current smart contract, and we can copy this exact smart contract that we are currently in to the memory. Then we have current gas price and operations on external smart contracts. In Fortis, we have block data, which is block hash, Coinbase, and Coinbase is the beneficiary address of the miner, and now with proof of stake is the recipient of the validator rewards. Then we have timestamp, block number, difficulty, and block gas limit. One thing to note here, as you can see, it was created on 2019 and difficulty is deprecated right now because we are in proof of stake. That means that there is no difficulty of mining the block because now we have validators that are running the nodes. And this opcode was actually replaced by prev_random, and this is just the random number generated by set of validators for each block. However, me saying that it is random, you should not use it as the source of randomness because it's manipulable by validators to some extent. Next up, we have stack, memory, storage, and flow operations. So pop does nothing, but it just takes the value out of the stack if you don't need them anymore. Concerning mloads and stores, we already discussed that, but those are very interesting instructions. And before going into them, we will briefly talk about the process counter. So in this example, when we run the code, you can see here what is here. This is process counter. So it starts at 0, and then with each byte that it executes, it adds 1. In this case, push 1 is the number, push 1 is the opcode to be executed, and 42 is the second byte. We can see it well if we are switching to bytecode. We have first, which is push 1, and then we have 42. So this is actually 2 words. So we are adding 2. The same here. mstore is like single word. This is the process counter. But we have operations jump and jump if that allows you to not execute the opcodes one by one, but to jump to any location that you want. So I slightly modified this example to account for this. And I use also jump dest because in EVM, if you want to jump somewhere, the jump destination has to be jump dest. If there is different opcode, it will crash. This is how EVM requires you not to land in any random place. So here, the normal stuff, we are just storing 42 in memory. Then we are pushing 4, which will be the process counter that we want to jump to. And you can see under 4, we have our jump dest. And if I did not make a mistake, it will work. Okay, cool. You can see that we switched from here. Now this is highlighted. So that means that we jumped from here to here. And I made a mistake because I jumped just before mstore, and because there was nothing on the stack and I wanted to, and mstore uses 2 operations, it crashed with stack underflow. So I can quickly change that with moving the jump test to the top, and then hopefully it will work. Jump, okay, we jump to 0, and yep, and we are having the infinite loop because here we are just jumping here and we are moving around and around. So actually this is what allows you to have any kind of loops in your program. Jump if is a bit different because it also takes a parameter that is either 0 or non-zero. So conditional jumps. Like for example, if you have a loop which checks if your iterator number reached the specific number. So if it didn't, jump again, and run this loop again. If it reached the expected value, just continue. Then M size, amount of available gas, and jump, the valid destinations for jump. Again, if you try to jump to some process counter number that doesn't have jump dest, the program will crash. We can actually do that by changing that to 1. That would mean that we will try to jump here. And if we run it, okay, we have 1 on stack, and we try to jump to the process counter number 1, the program crashed. So it will be the same if you are trying to execute this code in EVM. Next we have pushes, and you can see that we have like 32 pushes. The difference is that we are placing 1, 2, 3 up to 32 bytes. So if you want to put 5 bytes, you can use push 5. If you want to push 32 bytes, you are using push. The same with dupes, and again I already mentioned that we have only 16 dupes, and for me this is like bad design of EVM. There is like 16 dup application, and we at least should add additional duplicate operation that would allow you to pass a number from the stack to take the arbitrary value from the stack, because right now the most recent version of Ethereum, they solve this problem by moving the stack values to the memory, but as you remember, the memory expansion cost is quite high, and this would be way cheaper if we just use the arbitrary duplicate. But I guess that this was just easier to implement it that way, and probably the designers of EVM like stick with that. The same goes for swap. And next, logs. So logs and events are pretty much the same, because logs are meant to be saved off chain. You cannot read them on chain, and then you can query for these logs anything off chain that you want. And actually this is here called log, but in Solidity it's called an event. So you are emitting an event, but the underlying opcodes are log. And the same as with Solidity, you may have 0 topics, 1, 2, 3, or up to 4. So those are your indexed parameters. Next we have system operations. One is create, which just creates new contract, and it takes only 3 inputs, which is the value to be passed, input offset, and input size. And it takes offset and size. Those are meant to be read from memory. Next we have external call code, which is long deprecated, so you cannot use it in the most recent versions of Solidity, but still EVM supports that, so you can use that by writing EVM only code. So call code is similar to delegate call. Actually, delegate call was introduced later to fix call code, because call code works like delegate call, but it did not preserve message value and message sender. And this was problematic, and actually it was not useful at all to use that, so the delegate call was created and it was deprecated. And one important thing to know about delegate call is that it takes 1 less parameter than call, because it did not take message value. So message value is assumed to be preserved from the calling context. So you should be very wary if you are sending something into delegate call that the message value is actually not being passed with the call. Apart from that, we have static call, which is like normal call, but it does not allow for any storage modification. So those are all these pure and view functions that you have in Solidity. Return holds the execution and returns. So again, it's named the same as in Solidity. Revert, of course, also the same as Solidity. You are reverting. You are just taking 2 parameters. Again, memory offset and length to tell the byte array to return to the calling context. Next we have invalid. So it means what it is. It's just invalid instruction, and it's used by Solidity to split the actual code from the metadata during contract deployment. And the last one that we have is self-destruct, which destructs the smart contract. It's being deprecated. Still, you can use it in EVM, but there is the plan to totally remove that from EVM and not allow to remove code at all. Next up, we have precompiles. So those refer to predefined smart contracts that are included in the Ethereum protocol. These precompiled contracts are implemented directly in EVM using native code used to build EVM node. So you can call them like any other contract, but their address is symbolic. That means that you cannot retrieve its code like with any other contracts due to the fact that they are just a link to the underlying EVM functionality. They are designed to perform computationally expensive operations that may be required by various applications on the Ethereum blockchain. The purpose of precompiles is to optimize the execution of certain operations, making them more efficient and cost-effective. We'll see how Go Ethereum implements precompiles when we'll dissect its implementation later. So Ethereum has several precompiled contracts, and each is assigned a specific address on the Ethereum blockchain. These precompiled contracts are used for operations such as elliptic curve cryptography, cryptographic hash functions, and other complex calculations that are resource intensive. By providing this operation as precompiled contracts, Ethereum aims to reduce the gas costs assisted with executing these computations, making the platform more scalable and efficient. Additional note here is that the precompiled addresses are always considered warm. It will probably not tell you much yet because we didn't discuss the concept of gas in detail, but what you have to know for now is that whenever there is a need to read something from the disk, EVM charges you more the first time that you do it, and then it's cached, so all the other references to this value are cheaper. So what I will do now is I will go through all these precompiled codes. You can actually use EVM codes, which I use a lot. This is a great source when you are trying to play with EVM. You have all the opcodes, precompiles, you have playground, information about EVM, tons and tons of knowledge. Super useful. I use it basically every week. So one of the precompiles is Easy Recover. You may know that from Solidity because you have Easy Recover there. It is used to take the hash and signature of the user and verify that he is the person that actually signed it. And again, this is implemented directly into EVM. If you try to call it yourself as normal smart contract, it will do what it should do. If you pass the correct input, it will return you normal value. So you don't have to use Easy Recover. You can call it as any other contract. But if you are trying to get its code, you will get empty array. The code doesn't exist. We will see when going through Go Ethereum that the code is actually that there is actually separate path of execution precompiles and execution normal smart contracts. Next precompile is SHA-256, which is our Ketchak. And next, we have some precompiles that you will probably never use, which were created to comply with Bitcoin, with zero knowledge cryptography. One of them is RIP-EMD. Well, RIP-EMD, for example, is used in Bitcoin to hash the public key. So it was added here. Next is identity. This contract does nothing more than sending back to you whatever you send to it. It's like echo in, for example, in Shell. Why this is useful? Because in EVM there is no notion of copying memory. There is no specific opcode to copy one part of the memory to the other part of the memory. So that means that if you want to copy some memory to other part, what you can do is to call the contract with whatever memory that you want and save the return value in some other part of the memory. And actually, concerning all the others, I will not go in details because I've never used them, and you will probably not use them as well, because they're very specific to some usages like mod exp. I think that its only usage is in RSA cryptography, and you can use like EVM to verify that. ECAD, ECMul, and EC pairing are used in ZK cryptography, and the only known usage of that in EVM for me is Tornado Cache and their ZK part. And the last one here is Blake 2F, which is compression algorithm used by Zcash. So you can see that for the most part, these precompiles are used here because they are very heavy to calculate, and EVM wanted to be compliant with different chains and give you some way to communicate with other blockchains effectively. Yeah, I know that was long, but I hope that you learned something this time. So next up are transactions. I hope you liked it, and next up we will be talking about transaction. Stay tuned.